Please pay attention. Although there are still few people are not here, but I have to start because we have lots of work to do. You have your homework for chapter 6, which I already gave it to you, which is due next Tuesday. Everybody does. So today I'm going to finish the lecture. Everything that you want to know, actually all the problem that you are going to do, all of concept of it will be explained here by the end of today's lecture. Then we have another chapter, which is very important chapter, and that's chapter 7, which we have to put all the chapters together. So that means chapter 1, 2, 3, 4, 5, 6 come together as one problem. So as I said it earlier, so you see a post there outside with a light there. In that post, everything happened. Axial load happened, torsion happened because the wind blowing the sign away, it bending this way, bending that way. So that's what we are going to do in chapter 7. Very quickly, we have to understand, we come up with the state of stress and what we do with that state of stress, which is the subject of chapter 7. Very complex, very understanding, but without that, nothing will happen. In chapter 7 is the culmination of the whole system. Is that understood? So it's important today. I need to finish everything about chapter 6. You will see it is not that difficult. However, you have to pay attention to the following. We have had, I'm going to review that one more time for you guys, what we said last time. Is that understood there? So you already know that. You want to rewrite it, that's up to you or not. So you have here a beam like this. So we usually do not show the cross-section of the beam. The beam, like your quiz, for example, could be loaded like that. Everybody see that? Could have single load on the top, or P or M, doesn't matter. But when you cut it somewhere, as we did it last time, in that cross-section, so you show the beam now like that. This line only represents the neutral surface of the beam. It does not show the height of the beam. Now, when we go to the cross-section, you cut it left, right? This is what we are talking about. So here, if this was point A, for example, here you will have an RA there. Is that correct or not? Yes. And then, of course, you have some kind of load. You may or may not have that. You have seen that. Some of you missed that. Then in the body, this is the subject now. In the body, depends how this works, plus or minus. It may be going down or it may be going up. You have a shear force. We usually put it this way because this is according to our shear diagram, that's the plus side. Everybody, statically, that's negative. But as far as the shear diagram goes, that is a positive deformation, so we put it there. Now the question was, okay, if this happened, what is going to happen? This is what you want probably to put in your note, and that's good for chapter 7 as well. So what is going to happen to this point, or this point, or this point, or this point, or this point? Notice that there is shear there. Originally in chapter 1, we said tau equal to force over area, which we said it doesn't work because that one shows an average stress from top to bottom, which means the following. So let's assume this is the length of the beam from point A to point, let's see, I call that one B. So let's call it to point D here, as we did it before. This is only the beam from A to B. Everybody, of course, don't forget, there is a moment there as well. Everybody else. So if I want to complete that, so there should be an M there. But that was subject of chapter 4. This color one is the chapter 6 we are talking about, the stresses due to the shear. And now let's assume that the cross section was something like that. This was the cross section of the beam. Now I'm looking here, side view there. Is that correct or not? So we discussed that last time. I don't have to tell you that. This is still is your neutral axis. Is that correct or not? Then I said the following. If I want to calculate shear stress at this level, so this is, let's say, at the distance of y, I need to calculate shear stress there, which shear stress changes from here to here with this understanding that on the top shear stress was equal to 0. Why 0? Because of the following. If I'm looking at this state of stress there, which is this state of stress, let's call it point A. If I'm looking at that point, state of stress there, this is in reference that I was talking about before. Remember, always the tau xy must be equal to tau yx. We would that. However, since there is nothing here, is that correct here? There should be nothing there. So that's the state as far as this shear is concerned. I'm not talking about the moment, So I'm going to erase the moment. That's a different issue. Is that correct? That's when we combine the two together. Here we are only talking about the shear stress. This is shear force. Shear stress on top is 0. Remember that? Yes. Because what? Because there is no shear stress here. There is no shear stress there. There's 0. Then as we go down, the value of shear stress keep increasing until we get to the neutral axis. How does it change? This is the review of what we did last time by this equation. So it will be dependent on the I, which is the constant for this cross section, depend on the T. For this cross section, T is the width of the beam, which is constant, but sometimes that's not the C. We see it in example. Is that correct or not? Then the value of the shear will be given. So the only unknown really that you should worry about and would be about the Q. What the Q end up to be when you go to the equation sheet that I gave you was the integration of YdA from here to here. And YdA is Q. Is that correct? That was part of the equation that I didn't show it to you, but it is in your handout. Is that correct or not? Therefore, it becomes Q of that area with respect to neutral axis that everybody can calculate, because you all keep calculating y bar. In y bar, you are using the Q all the time. Is that correct? That's the same Q. Is that correct or not? If you understand the math part of it, that's all you need. As a result, look at it. If I am at this level, there is no material above me. So the tau must be equal. The Q is 0. The tau is 0. As I go down, Q keep, area keep increasing, but at the same time, Q keep increasing, and it is not linearly increasing. The value of the Q is not by y. It is because it is A times y. Is that correct or not? Therefore, it's a parabola, and the maximum here, you don't need to go below that, because after that, the Q becomes negative. You have to subtract. Is that correct? So you go from here to here, or you go from here to here. That's the same thing. Is that correct if it is symmetrical? Now let's do the example. Now, see, this is important because this is the result. But people, if I give you this equation with nothing else, that's no good. The only thing you need to do all your homework is this and that. Everybody understand what I'm saying there? So at that point, we need to calculate the value of the shear in the cross section as we go from top to bottom, knowing top is 0. Is that correct or not? Now let's go to your handout problem. There are 3 problems there. We are going to solve all of them. You need your handout in front of you, everybody. I don't have extra one. Actually, these are pages 2, 3. I gave you page 1 because that was in color. I wanted you see the derivation of the equation. Is that understood? Yes? However, from now on, we are going to go through the example. I keep this here. Again, the concentration should not be on this one. This is understandable. This is very simple. Is this and that is the idea there. Anyhow, we have there a beam there given to you. Quickly go over the number there. So I'm going to put it here. So we have a beam here like this. And I believe there was a force here, 8 kips. Is that correct or not? Yes? Because I changed it here. Is it 8 or 18? 18? 8. Yes, 8. Yeah, there is 8 kips there. Then there is another. This is not in this case. There is another one, 18.5 K here. And then this is 16 inches, 10 inches, and 16 inches. Obviously, exactly what I said, some of you missed in your first example. Before you do anything else, you have to find a reaction. Without reaction, you don't have anything there. So, of course, one of them is roller, one of them is spin. And as I said, unfortunately, several people missed that in the previous quiz. That is first step of every static work. Is that correct? Nevertheless, this becomes equal to 12K, and the balance of it, after you take the moment, I'm bypassing all of that. The rebalance of that will be 14.5, so this will be 14.5K. And then if you see in the problem there, I have cut the beam somewhere here, and I asked you to calculate stresses in that section. But I did not give you the distance. Why? Why didn't I do? Does it make any difference there? Yes or no? And this goes back to, does not make any difference. Why I don't need the distance? Generally, we do need the distance here, because from here to here, shear is, the value of shear is constant equal. Remember the shear and moment diagram? No matter whether I cut it here or here or here or here, the value still is 12 going down, which is positive. Is that correct or not? So the value of the shear, this is the first question you want to answer there. For this problem is 12 kips, and it is going down in the cross section like that. Is that correct or not? Yes? Statically negative, diagram-wise, shear diagram positive. Is that understood? This is the difference between the two. Then I need the cross section. So usually this is, as I said, this is the centroid of the cross section. We are giving you this cross section for this beam. So the cross section is 1 inch by 4 inches. And then it is like this. I'm sorry. 2 inches by 4 inches. And the height are given like that. Oh, I can put here 4 inches and 2 inches and erase that one. We don't need that one. Okay, what do I need next? You see, this is what I said last time. What I need here is I with respect to the neutral axis, which coming from the moment idea. Is that correct or not? Yes? So therefore, I have to go back to the same routine, which you have to do it for every problem. And those are calculating the y bar and moment of inertia. I told you this. Some of you missed it. Some of you are still not aware of parallel axis theory. As commonly as you calculate the area of a circle or a rectangular, for a stress analysis, you have to do y bar and moment of inertia. We thought that you cannot get anywhere, so might as well learn it. And if it is not too late, do it this weekend. Is that understood? Many of you are okay, because you know your parallel axis theory. So I'm not going to do that. So when you do that, you put here a y bar. You put here an x-axis, and if this is the centroid, you call this one y bar. Anyhow, for this problem, where you take the q of that and q of that with respect to x and divide by divided by the area, then you will see that the y bar become exactly equal to 2 inch. Purposely done that way to show you something important here. So in other words, the centroid is not there. The centroid is here. Therefore, your neutral axis is there. So therefore, y bar here equal to 2 inches. Okay? So now I need to calculate I. Where do I need to calculate I? With respect to this neutral axis. Both of them need parallel axis theory. This is a special case. I can use the other number. This is on the base of the rectangular, so the answer I is 1/3 of base time height cubic. If you want, you can use that, but you don't need that. You still can use parallel axis theory with the same result. It's a little bit more work. However, for both of them, since this is passing through the base of this one or base of that one, therefore you can use 1/3 of base time height cubic. That's the exception to the parallel axis theory. Nevertheless, I'm not going to do that. So that's up to you. That I become 32 inch to the power of 4. Y bar, I, essential part of this stress analysis. Probably will happen in the final 2. So is that understood? 1 or 2 or 3 problem, I don't know. We will decide that what kind of question is there given to you. Next is what? Next is calculating the tau. But the tau is different from different point, yes or no? So what they are asking you to do, they are asking you to calculate shear stresses at A, and they are asking you in this question, find the shear stresses at B, and they are at 1 inch distances apart from top. And then at the end, if you read the question, it says plot the distribution of the shear stress. How is shear stress going from top to bottom? You already answered me. That distribution is with Q, so it is a parabola. It is not a straight line. It's not like moment. The moment was 2 lines, one going up, one going down. This was linear. Is that correct here? Here is a parabola because Q is not, Q actually is area times distance. Everybody see that? Yes? So now let's calculate that. So I want to calculate that based on what I did here. So what should I need to do? I need to define this line. Is that correct? That line for A is this. So in other words, you make here a cut similar to a cut there. You draw a line there. The area above that is the Q. That little cut will be the T. Is that correct or not? So you are cutting, in a way, this much Q from the rest, and you look like that. You are looking for shear stresses going vertically and shear stresses going horizontally based on your state of stress. I did not finish that one. So for the second one, for let's say for point B here, for that A was 0 because it was on top. If I go at B, I see this going down, yes or no? And on the other side, I should put plus and minus, and then like that. So we have done that before several times, so you know what I'm talking about here. And that tau technically is a negative tau, everybody. Although the shear force was positive, but it gives a negative tau. What we don't worry about this until chapter 7, because in the chapter 7 you have to come up with the right sign. Is that correct or not? Here, just give me the magnitude as I'm going to do it here. So we need the tau at point A, correct or not? So to do that, I need one quantity more, and that quantity is Q for that level. Q of that level is the Q of that little area with respect to neutral axis, which is, come on guys, give me the number. 1 times 1 times what? Times 3.5, correct? Many of you quiet. You do it all the time for Y bar. Now I do it here, everybody panic. So Y bar, when you do this for Y bar, you see this, you say this times that, multiplied by that. Is that correct? All the time you do it for Y bar. Yeah, that's the same Q, guys. Okay, A times Y. Is that correct or not? So it's 1 times 1. You put the mass here as if it is a mass, and you take the moment about the neutral axis, which is the distance of 3.5. Yes or no? So what's the unit? The unit is inch to the power of 3. Remember, we started with the area, then the Q, and then moment of inertia. Inch square, inch 3, then inch to the power of 4. That system, I showed it to you many times in the past. Is that correct or not? Therefore, that's it. The QA become equal to, write it down here. QA become equal to how much was it? I had it somewhere else, so let's not get my other person. So it become, I believe, 3.5. That's not what I'm looking for. Inch to the power of 3. I don't need any number there. That's right. Inch to the power of 3. Correct? And then we have to calculate tau A. So we're calculating tau at that level. So understand what happened here. Tau A means this shear stresses all the way like this. Is that understood? Yes or no? Correct? Across this way is constant. This way, like moment, is effect of moment, which is sigma variable again. Is that correct or not? That tau A now is become equal to tau A. Can you see it from that corner? Tau A becomes shear force. The shear force was 12K. This is the first time, so I put the unit in. Multiplied by Q. The Q is 3.5 inch to the power of 3, correct or not? So it becomes kips inch to the power of 3. Then divided by I. I was or is 32 inch to the power of 4 multiplied by T now. The T is, no, the 3 is this cut, the thickness of the beam. The T was this T. This was the thickness from here to here. The T is 1 inch. Is that correct or not? This one inch, not that one. So therefore, times 1 inch. So that is inch. So it is inch to the power of 5. This is inch to the power of 3. The result is kips over inch to the power of 2, which is unit of stress, which is KSI. Is that correct? Kips per inch square, which become equal to 1.31 KSI. Okay? That's for A. Now, for B, my question to you before I do it. Because for B now, look at this distance become twice as much. Yes? Can I multiply that by 2 and say that's the answer? Yes or no, immediately? No, because it is not linear. If it was linear, I could do that. Everybody understand? Linear means similar triangle. Yes, or it is a parabola. I cannot do that. Therefore, I have to recalculate the value of Q, because this is granted. This area is 1 by 1. This area is 1 by 1. So the area is twice. But Q of that and Q of that with respect to here is totally different. Everybody understands it? Because area times Y, and Y are different. Is that understood? So therefore, this question number 1, calculate tau at A. We did it. Now we want to calculate shear stress at B. So let's do it. This time, everything is the same except Q. So you can do it in one formula. So tau for B equal to 12 kips. So I don't have to use unit. I leave the Q at the end. Then 32 times, again, 1, because this cut there. Now, this time, I have to cut it like that. Is that correct or not? Yes? Some people want to do that. They calculate Q of that and Q of that added together. Might as well do the Q of the whole area, because that's the above that cut. Is that, remember, every time you do that, you need the all the area above. That's the whole scenario. Is that correct or not? Yes? So this time what the Q will be. Now, give me quickly now. You have to become quick on that one. 1 times 2, that's right, 1. Just give me the number. Some of you are guys, by the way, I have noticed this is, I have to mention because somebody says 6 to me. You put 6 here, this either correct or not correct. If it is correct, okay, you get the credit because you know. If it is incorrect, I do not know what mistake you made. Some of you are already doing it that in quizzes. I keep mentioning it. Put the number down, because you need to give me how you are calculating in order, if you are making a little mistake, mathematical mistake, I can recognize that and give you more credit. Everybody, by putting 6, you either get 0 or the whole point. Is that understood what I'm saying? If it's 6 is not correct. Yes, 6 is correct because it's 1 times 2 times what? Time. The centroid now is here. Is that correct? Time? The 3. Is that correct? So you said that quickly. That's very good. I like it, but put it there. I put it this way. Don't put 6 there. That's what I'm saying. Okay, so therefore, you get this one. You calculate that one. This one ends up to be 2.25. Actually, it's less than twice. Everybody see that? Because the Q is just... Then I asked a student, I don't know whether I asked the student, but I forgot what I wrote there. Then I asked the student to plot this. Is that correct? Or I calculate what the maximum shear stress. Where is the maximum shear stress? Maximum shear stress is on the, for this problem, is on the neutral process. So I have to repeat the process one more time and do it for point C, which is the whole area above it. Is that correct or not? Yes? So repeat one more time. The tau at C become equal to 12. Everything is the same, 32. Here, you will look at this line I draw that. The thickness still is 1 inch. Yes or no? Correct. So time 1 inch. The only thing is changes is the value of the Q, which will be the entire area, which will be 4 times 1 times what? Times 2, which become 8 inch to the power of 3. So then you calculate that one, and that one become 3 KSI. So this is KSI. Correct? So we already have calculated the shear stresses at point A, B, C. Of course, shear stress here also is what? No answer? Shear stress here. 0, of course, that's what I've said. On the top and on the bottom, it is 0 because there is nothing underneath, nothing on top. Everybody understand that? So this, now we are plotting it. Here, no, I want you to understand one more time again. Shear stress is going like that. This is a little bit larger. This is the highest value like that. Is that correct? What I'm trying here to plot, the plot is intensity of that one. So the shear stresses are in the section, but we plot it like a parabola, yes or no? So therefore, don't assume the shear is coming out. It's not like moment. So if this is point, the top, and this is point A, this is point B, and this is point C, and this was D here. So for example, you want the point D. What we got so far is the following. We got here 1 point, how much was it? 1.31 in KSI. Here we got 2.25 KSI, and here we got 3 KSI. Yes or no? In magnitude. So the change in the magnitude is a parabola, yes or no? But don't assume again, it's not outside. The shear stresses are in the body going downward. Is that correct or not? Yes? Okay. Now, if here is 0, and I ask you to plot this, many people do this. Is that correct or not? No. Why not? What? No, it should be correct. If there was not picture like that, it was a rectangular shape, that would be it. That would be the whole parabola from top to bottom. The reason is not the same is this guy. You look at point C. You are an epsilon above, the thickness is 1 inch. You are an epsilon below, suddenly the thickness becomes 4 inches. So if you have an item like that, it's obvious. This is logical force. Actually, this is what happened to the building as well. So therefore, you have a column here sitting on a foundation, which is much bigger. Is that correct or not? And if the horizontal force comes like earthquake forces or wind forces, where do you think column is going to shear off? It's going to shear off at its base. There is no reason the foundation, which is much bigger in thickness, to be shear off. Everybody understand that? There's no. So therefore, this is not true, because if I go at this point, this was the tau for C minus, because I'm a little bit above that. Is that correct? If I go a little bit below, everything is the same. Q is the same, everything is the same. What is changing only? Instead of 1 inch, I would have 4 inch. So I'm going to adjust that one more time with color. So this is what's your, if I want to calculate tau, you should rewrite it, but here, this becomes 4 inch. Obviously, this becomes much less. That's what the foundation does not shear off. The column will shear off on the top of foundation. Is that understood? That because suddenly the thickness instead of 1 inch become 4 inch. So this stress becomes 0.75, 1/4 of what is what. Because the T is in the denominator, so it becomes 4 times more. The stress becomes 1/4 of that. Yes or no? Therefore, the diagram goes like that. The diagram goes from here to here. A parabola here is 0, but here for the lower part is 0.75. For the upper part is, which is the column versus foundation. Did you see that? Correct? Everybody with me? You are awfully quiet. What does it mean? Very simply, when I'm here and epsilon below and epsilon below, Q is the same Q. Is that correct? Shear is the same thing. The only thing is changes 1 inch versus 4 inch. That's what I did. The color one is in the lower part. The black one is on the upper part. Of course, you never be concerned about that one. You will be about. However, this is important for future, for design issue. Now look at the second problem. Now, can you look at the second problem there, and can you see the distribution, shear stress distribution? What happened to shear stress distribution? Can you tell me why now? Because the thickness of the beam. Now I'm going to explain that for the idea of everything. So before we go into detail of that, these are the important part. So let's erase that. Go back again to here, to this shear stresses here, what happened there. So I want to show you what happened there in the sideways. So if I want to show this beam in this direction, the beam was like that. So please draw it like that. Exactly where we were here. So this was, I needed my beam, but I crossed this. Here. We cut, here was our beam. This was A was 12. This was our shear. And this is the beam, which looks like that. Is that on the side view? So if I show this a little bit bigger, this will be like what we did there. This was 12K, and this was point A was here, point B was there. Everybody see that? Then you see a line here because you see this line from the side. Is that correct or not? Then there was a point here, there was a point there. One little bit above, one little bit below. This is for the purpose of chapter 7. This is what we call it the state of stress again. Notice I can add one more point here, and that point was here. At that point, if I want to show the state of stress, the state of stress is 0 and 0. Remember that we said that. When we come to this point, I'm going to show it now a little bit bigger. If I want to that point, this was point A. What did we end up there? Stress is going. This is inside the beam. Nobody is going to be inside. You are always on the outside. This is outside, this is inside. But you look, this is a beam. You only look at the outside of it. All of you, you have seen this before. Everybody, you are not inside the body. The stresses are in the body. The effect is on the outside, you are plotting it for outside. Yes or no? We did that for everything that we did in the past. So here, what was this? The shear stress was this quantity going downward. So you put it here, correct or not? On the other side, you put equal and opposite, and so on and so forth. Notice, don't worry about if you go to the other side of the beam and you do the same thing. So you can use the free body diagram of left side. You can do it for the right side. In this side should be equal and opposite. We have said that. So one side is going down, the other side, oh, I'm sorry. This was one down, this one should be up. Is that correct or not? So the shear stress will be like that. So we see this side versus that side. Is that correct? So that means you can come from the right, you can come from the left. Is that understood? That does not make any difference. However, the shear stress for this one in magnitude is equal to how much? In magnitude is 1.31, but actually it is a negative. Yes or no? Because this is a negative format, correct? So this was, if you want to go to chapter 7, please write it down. Tau equal to minus 1.1 KSI. And that is as far as the shear is concerned. Now, obviously, if there was a moment, I have to add the effect of moment as well, which is a sigma. Remember that? That we will talk about it later on, but you can already appreciate that there might be a moment here. If it is compression here, it pushes that way. So there is a sigma and there is a tau combination together. Just hold on 1 second. I'll do it. No, we go to the B. This value changes to minus 2.5. You go to this C minus, which is the top one. This 3 KSI here is 0.75. What's the question? This state of stress is negative. Refer to your note. I have mentioned that at least 5 times. Believe me. It is in your note all over. This state of stress has nothing to do with the shear force and shear diagram. Shear diagram is totally a different convention. Everybody understand that? I said many times, look at your note. Anytime the tau goes like that, you should put it here. Yeah, this tau is still there. Look, this tau is negative. This tau, this is the sign convention for the tau, which I mentioned it many times, several times. That's the sign convention. What you are thinking about the shear force. Listen to me, please. You get what? Why do you think this is different? Why should it be different? Because you are thinking of the shear force, which was positive. Yes or no? The positive shear force actually gives you a negative shear stress, if that's what you want to do. Yes? Okay. And this sign convention for compression, I already signed for the sigma. Sign convention go with the tension and compression. For the shear, this is the sign convention. I believe I have mentioned it 4 or 5 times in different occasions. Is that understood? Yes.
So when we were asked to find tau max, it's going to be the 3 KSI.
Correct.
And then when we're doing the shear diagram is when we're going to need to know that
shear force.
The shear force.
The diagram is for shear force, and it has a different sign convention that shear stress.
Then we're going to need to find where it equals 0.75 to go to
no.
draw the shear.
0.75 is just stress here versus here, which has nothing to do with that.
I think she's asking, are you going to ask us to plot the shear stress distribution on the button?
This is the shear. I did it. I erased it.
No, yeah.
Oh, I haven't done it? I erased it. Yes. This was the shear stress distribution.
So on the final, we'll...
That's it. I asked that question before many times. Yes, that's the shear stress distribution because you have to calculate all the value. Now I'm going to talk about next one. So look what the next one is. This one clears more stuff. Now his question was different. So this question is still questioning what is the sign convention for tau, which has been mentioned before many times. So everybody should refer to that. The tau shear, if shear stress is going like this, it is the negative. If go reverse of that, it is positive. We have talked about that many times. Now I want you to look at this problem, which I'm not going to do it because it's so obvious. Of course, look what happened here. Now, the same ideas all being represented there. Here it is, guys. So you have a cross-section. Again, this is the cross-section of the beam. Is given like that. Is that correct or not? Yes? Again, this is part of a diagram. You go to a shear diagram, and to determine, especially for you asked that question, I still don't know why you ask that question again. Shear diagram has the sign convention of his own. Everybody understand that? So again, one more time. If the force is going, this is what he probably were asking, still is not communicating with me his ideas. So here, if there is a shear going down, this shear is positive. But this stress, if I'm looking at that stress become negative. If you agree with that. If that was what you were thinking, that's the answer. The sign convention, this is the way they decided. If it goes like that, we are going to call it negative. If reverse of that, this is the sign convention. As if tension is positive, compression is negative. Maybe if you go to one of the stars there, maybe they call it reverse. Tension is negative, compression is positive. This is our sign convention universal. This is what we decided. But you have to remember that. This is negative. Reverse of that is positive. Anyhow, now we go to here. This is again part of a beam. It's given. That, of course, this is symmetrical. Therefore, you don't need to worry about the y. Is that correct or not? Yes? Then you have to check the moment of inertia. I give you, because I don't have time to do it, because this is simple. You take the moment of inertia of that, and this, and then add it together. I become 155.6 times 10 to the power of minus 6 meter to the power of 4. Is that correct or not? Yes? But then they are asking you to calculate shear stresses here, here, here. Why here? Because there is a little bit change. Actually, there is a lot change here, because this thickness usually versus this thickness has a ratio of 10 to 1, 15 to 1. Therefore, as I go down, look, I don't have to do that again here. As I go down, here is 0, first of all. Here is 0. In between, I have to find the shear stresses. So as you can appreciate now, I'm going to erase that and use this is again the distribution. The shear stresses are here. Everybody see that? Yes? Start here, 0, keep increasing. Suddenly it become here larger and larger, and the shear stresses, these are not shear forces, these are shear stresses, which is distributed like that. So shear stresses on the neutral axis for this beam become the largest, because the Q become the largest value. However, there is a big shift when we go from this part of a beam to that part of a beam. Why? Because this thickness and this thickness suddenly changes. Is that correct or not? So therefore, when you plot it, it goes 0. The Q keep increasing it. Okay, it goes like that. But at that point, suddenly it's going to have a ratio of 1 to 10 or 1 to 15. Depends what thickness I give you here and what thickness. Usually for beam of this one, if this is 3/4 of an inch and this is 15 inch, you see that how much really huge difference between the two. And then it jump, and then of course Q keep increasing, but only little bit. So it go a little bit like that. So it goes like that and like that. So we have two break here, one here, one there, because of the change in the two. Is that understood? Yes? So you can calculate now. If somebody asks you to plot this, all you need shear stress at this point, one of them, not two. The other one, you just multiply it by ratio of this T to this, because this T will be given to you. We call it this, actually this is called flange. This is called web for future reference. So the thickness of the web will be given to you. The thickness of the flange, which is this one, will be give you to this, so all of that. And there are another thicknesses here, which is when you go down. Everything will be given to you. But what is important here, there is like what we saw there is a shift here from little one to a larger one. So in other words, remember what we designed this for? You designed this part of it just for future reference, for the normal stresses, because normal stresses are higher here and here. The shear stresses are more on the, look at it, look at the shear stresses. The shear stresses, the web actually is for the shear stresses, and the flanges are for normal stresses, combining the two. But you don't have to worry about it. These are extra information. Everybody understand what I'm saying? That all you have to do, if a question comes, plot that one. All you need to calculate, at this point is 0, that point is 0, only this and that. That's it. Is that correct? Of course, you need that one as well, because that one where you calculate Q of this plus Q of that. Is that understood? Yes? So this is a very simple problem. I just want to show it to you, because this one, you saw how the shear distribution changed. You saw that? So you can apply it there. Is that correct or not? Now let's go to the third problem, which is the part of half of your homework is related to that. And this one is a little bit different, so I'm going to change that a little bit or do it in a format that you guys all understand. By the way, is there any more question? Because somebody may have question. Anybody question? Any question? Everybody okay with this? All right? So notice for chapter 7, we need to come up with this, and we need to come up for sine. Here, in this chapter, if you just give me the number, it is okay, because they do not want you to come up with a sign, because that happened afterwards. For chapter 7, I put it there, sign there, so for you to follow that one. Now, here is the next problem, which is very important problem, but also the same principle applied. Let's say this time you are making a beam, a wood, but it is made of wood with the following dimension. So please write it down. So here it is, symmetrical again, both ways, both in X and in Y. So here it is 120, I'm sorry, 120 millimeter here, 20 millimeter there, 20 millimeter there for the width of 160 millimeter. The height are 20, 20, and 160, which is the height of the beam is 200 millimeter. Here is 160 millimeter, and it is made of wood. So if it is wood, I have to think about connecting this piece to this piece and this piece to that piece, yes or no? One option I have is to glue it together. Now, what is the glue acting one? What's the glue is for, guys? What? What for? Remember, the whole idea was that we had, when we had the shear stress is vertical, and because of this, everybody see that? This is the vertical we were calculating. This is the horizontal. It means there is a horizontal shear going that way at layer by layer by layer. That's what I was showing you last time. So if I have a beam like that, several layers, I have to, as you see it here, you see that everything being glued. If it is not, if I bend it like that, all becomes zigzag at the end. Is that correct? This act like a one piece. However, this, as soon as I do that, there are stresses vertically in the cross section, and there are stresses horizontally, because tau xy must be equal to tau xy must be equal to tau yx. Is that correct? Everybody agreed on that a long time ago. Correct or not? That's why we have to. Therefore, if this is part of a beam, remember, this is the cross section of the beam goes like that. I don't want you to make a mistake. This is still is the cross section of the, is the box. You don't see it from outside. From outside, it looks like a square. Everybody understand that? But the beam is like this. Is that correct or not? Yes? Sitting on some kind of support. This is the height of it, and this is the width of it. Is that correct or not? This is what I'm talking about. Everybody see what I'm talking about? Yes? First of all, let's make that understood. Correct? So, but I don't show that because some people make mistake. That is still the cross section of the beam, and the cross of the beam will be subjected to some kind of shear force. Here we give you a positive shear, again shear going down. I have given the number of 3.5 kilonewton. Yes or no? Now I want you to calculate, this is, I call it, I don't know, A or B, I forgot what is there. So A, I believe. At that A, there is a glue there, connecting the two wood together. Yes or no? What's the shear at that glue? What kind of glue do we want? Do we want tau at point A? That's the first question we want to answer. Let's go step by step. Now, I hope that everybody understood what I did here, because this was simple enough. Is that correct or not? Don't worry about that discontinuity. Anytime the thickness changes, there is a discontinuity, it's obviously, because T changes. Yes or no? Correct? All right, how do we calculate that? Now, remember that the upper piece is sitting there, and these are the lower piece. The upper piece wants to move like that. Is that because of the horizontal or shear stress? Yes or no? Exactly like this glue, correct? So therefore, that glue, I need to calculate tau going that way, but that tau going that way is the same as tau going this way. Is that correct? So if I calculate one, I have calculated the other one. Actually, in the derivation, first I calculate tau horizontal, then I make it equal to vertical. I don't know whether you look at it or not, because the two are equal. Tau xy equal to tau yx. So the upper part of this beam wants to slide on this too. Is that correct or not? So to calculate that, I need to calculate shear stress here, which is vertical now, or horizontal. Yes or no? Therefore, tau at glue, write it down, which is at A, glue A, is equal to, let's put it all in one. So I'm going to put it all there in one equation because it's very simple. No, you need more note. Please go to your note because there is more involved with that problem than what you see here. Go to your note. Don't go to that page because there are not enough room to put everything there because there is more subject coming based on that homework. Okay, so tau is equal to VQ over IT, yes or no? What's the value of the shear? This time I'm going to in numeric, so I mean in the metric system. So therefore, you have two versions of it. That was inches and pound. Here is Newton, kilonewton, etc. So do not make any mistake. This is 3.5 times 10 to the power of 3 Newton. Is that correct or not? That's your shear force. Then I leave the Q at the end. Then I need the I. I need the I of this one. Everybody understand that? But that I'm bypassing again. So we calculate I of that one become equal to I put it here. I with respect to neutral axis become equal to 52.7 times 10 to the power of minus 6 meters to the power of 4. So I put the I here, 52.7 times 10 to the power of minus 6, which we did it here 2-3 times. Is that correct or not? What else do I need? I need the Q and I need the T. Is that correct now? Now you have to be very careful what Q do you want to. Since we are calculating the shear at this level, obviously anything above that will be the Q. Is that correct or not? So the Q will be this Q, but I have to cut both of them. Is that correct? In order to separate this, you cannot make one cut. Everybody understands? It's not yet separated, because if it was to slide, both of them have to slide at the same time. Is that correct or not? So you have to make a complete cut. So please be careful here. What we are saying here is very important. I'm going to show you here one more time. The idea was this. If you have a cross-section like that, all together, first of all, this looks, jokingly, sometimes I said this is a piece of cake. You want to cut a piece for yourself. This is what's going to happen. Let's say this is a cross-section of the beam, and you have a shear force here. Yes or no? When you want to calculate shear stresses, this formula, you can use it anyway. You make a cut like that. You haven't cut any piece out yet. This is not separation. You see, it has to be one piece separated from the rest. See, so if this was a cake, I will need a piece of cake. This is not going to do me any good. Is that correct or not? Therefore, I make a cut like that. Is that correct? Now, this piece is being totally separated. I can put it in a plate. Is that correct or not? Yes. Just to understand that. So this area that I cut away will be the Q. Everybody, this distance that I cut will be my T. However, as I said, one more time, you take your knife and do that, you have no piece of cake. Is that correct or not? Yes? So that's what I'm saying, though. In order to separate that part from the rest, you have to cut it totally. Everybody understand what I'm saying there? However, this doesn't make sense because the stresses here and here and here is different, but the stresses this way is constant. So usually we use it, cut it horizontally. Everybody understands. There is no sense to cut it like that unless it's a piece of cake. That's a different story. Is that understood? Yes, because the stresses, remember, horizontally were constant, vertically keep changing. So I make a cut like that. Who wants that average of that shear stress? That doesn't make sense. But that was for the purpose of saying that you can do that. Is that correct or not? The piece has to be, write it down in note, totally separated. The piece being separated will be the Q. The length of the cut, the where knife is cutting it, will be the T. If you do that, then all of the other problem becomes simply follow that rule. So look, I put a knife here, and I cut this totally away. So this is the Q. Now what's the T? Look at it. So this, that's what I want to understand, that if this give you in the book T equal to 20 millimeter, you don't put there 20 millimeter. You put Two of them, that's right. The T is symbolic. Is that correct or not? They're like there. The T, you just have, that's why I'm explaining all of that this way, because I have seen a student make a mistake there. They say VQ over IT, T is 20, they put 20. Of course, it's wrong. T here is this, and that to be separated together, altogether. So obviously, it is 40 millimeter times, of course, 10 to the power of minus 3. So you want to make it in meter, correct or not? Or you can put the 0.04. Is that correct? Then I need the Q. What Q do I need? Q of that with respect to the neutron. Now you should be very quick on that. Come on, guys, give me that Q. You can do it separately or you can do it here. I'd rather you do separately, put it there. But here, lack of time, we do that. What's the Q there? Come on, guys. 20 times what? 20 times what's this length? From here to here is 160 times what? 90. Times 90. Perfect. But that is in millimeter to the power of 3. I need to change it into meters, so I have to multiply that by 10 to the power of minus 9. Or we can put that in front of it, so it is better. So that's it, times 10 to the power of minus 9. Yes? What?
Where'd you get the 160?
The width, I mean this way, 20, 20, and 120. Here it's given at the beginning. This length is 160. What do I divide? Oh, I put 160. No, this is correct. Are you talking about 160? No, what 120? This is 120 given. This is 20, 20. So this length is 160. What? No, 120 at the middle. From here to here is 120 plus 20 plus 20 become 160. You don't want to spend time doing that kind of question. Come on, guys, you can ask me something much more important than that. Okay, that was explained at the beginning. It is in your handout. It's there in your handout too, and probably you don't have the handout. That's why you can go to the width, total width is, this is a piece of wood, 20 by 160. This is 20, that's 20. 100, but this side, the whole thing becomes 20, 20, 120, so the total becomes. So this is not 120. This is total is 160. Maybe that's a mistake. 120 is for the inside. Okay? So of course you know that. So let's go with this one. So that is, so look at the beauty of that. If you do it this way without this to the power of 5 or to the 7, this and that drops out. So this is, you do it this way, it is much simpler always, and the stress become equal to tau at A become equal to 359 kilopascal. So there is a 10 to the power of 3. So that become, usually we express the stresses in the wood in kilo, in the metal we express it in mega. Remember that? We did that many times. Okay, so that was easy, correct? Of course, the glue here and glue there is the same. Is that correct? So you don't have to do it. You either do it for top or bottom, unless it is different size or different format, is not symmetrical, then you have to check both glues. Is that? Now, you go to the market, you don't find that kind of glue because this is a heavier beam. Now, for furniture, sometimes they use the glue. Everybody sees that. Sometimes they use the bolt and nail, etc., etc. So it depends on what kind of shear forces you have. So if this is beyond the limit that you can find, of course, we have industrial glue, we have regular glue. Everybody understands that for different purpose. However, none of this work. What should we do? That's what you see in your handout. What should we do? We put there a nail or a bolt there. Everybody see that? Not gluing it. So glue goes away. So in other words, I'm going to put a nail here and nail there, which will change the problem. So discussion, the subject today is nail or bolt or connection between the 2-layer or 3-layer of the beam. As you saw in my handout, it still is here. This connection right now is glue. Everybody understands. There are not 4 different. From that probably you don't see it, but this is 4 different layer put glues together. Everybody said to make it one beam. And if I go, actually I have ruined it too. So if I push it too much bending, this glue sometime will come off. Is that correct? Because it is under shear stress. So if it is not glued, then I have to nail it. And nail it has a spacing, correct? So let's decide on that first. So glue has gone out. This was actually exactly what I did there. There was no difference except was in metric system. Is that correct or not? However, the problem was exactly the same. That was not the idea. The idea is to show you two things here. Now, if I look on the top of this beam, this is the top view, guys. So this is the top view of the beam cut, because this beam goes like that, and there are nails here. Everybody see what I'm talking in that level, like that, going like this. Is that correct or not? So there is one nail here, one nail here, one nail here. You just space it like that. Usually put it on the same side. Is that correct or not? So there is a spacing between each nail. We call it S by S. So in this scenario, the spacing between the nail, this is top view. When you write it down in your note, this is the top of the beam. So here, these are the layer. This is the top of the beam, but I do two there. Is that correct or not in each space? The question right now is two things we want to answer. What are forces in each nail? Force F, force in nails. And two, of course, question number two, question number one. And question number two is spacing, which will usually be a spacing S, which will be given to you. Sometimes I give you S, ask you to calculate F. Sometimes I give you F, ask you to calculate the spacing of the nail, how much is spacing. No, everybody have seen in the construction, carpentry construction, or the structure of 2-3-story building, that when they have the plywood there, they put the nail in 4-inch interval, and the inspector all come there to check to see where the contractor put the right size nail. That means you have to the nail should be able to carry certain forces. Now, what happened to this nail? Are they under normal stress or under shear stresses? Look at it. This one wants to move this way, yes or no? And therefore, because they are horizontal movement, correct? Because of tau yx, is that correct? Or therefore, these two nails will be in shear, which replace the glue. Is that correct or not? That's the question we want to answer. Now, before I answer that, there is another formula in the handout, which I will not discuss it, so I'm going to give you this little example for you to understand what that is, and everything is based on this little Q. Little Q, put it down in your note. We are going away from that first to understand what the Q is. If you understand what the Q is, the rest is simple, because the rest is, quite frankly, a high school question. However, you have to understand the value of Q, and many people traditionally do not understand what Q is, so I decided to give you this example. A few quarters ago, I decided to give the student this example to understand what the, first of all, Q is called shear flow. That's the name. Don't worry about it. Whatever you call it there, that doesn't matter. You can call it something else if you want. The shear flow, what does it mean? Nothing. Everybody understands. Unless you significantly understanding what that come from and how. In order to understand that, I'm going to put two pieces of the wood on top of each other, as if they are touching each other. And I'm going to put here 1,000 pound force here and 1,000 pound force here. I'm not using that equation, tau VQ. We are going back to chapter 1, trying to find out the shear stresses between these two wood. Is that depends on the size of this wood. Is that correct or not? Let's assume that this is 10-inch long, and let's say that the width of that is 5 inch. Everybody see what I'm talking about. So this load actually applies to the upper part one. If you want to go three-dimensionally, you don't need to go that. I'm showing you that you be careful what we are doing that. So upper part is being moved to the left, 1,000 pounds, and the lower one is moving that way. Yes, so then you have to show me the free body diagram, either the upper part or the lower part, which is very simple. Okay, here we go. So here is the lower part. So this is 10 inch, this is 5 inch, and this is the system. And here is your external force, which is 1,000 pounds. Is that correct or not? Yes? So obviously, if this is lecture 1. Everybody, the lecture 1, we had this problem, yes? We have here a shear force of how much? A shear force of 1,000 pounds going reverse. That's very simple, static, basic, very simple. Now, what is the shear stress in here? assuming it is average, not the other formula. What's tau average here? I put it in color. What's tau average equal to? Force over area, correct? So how much force do I have? 1,000 pounds. How much area do we have? 10 and 5. Yes, sir. 10 and 5. So therefore, inch, 50 inch, 1,000. So we have 20 pounds per inch square PSI. Is that correct? The shear stress, correct? So if I get here, guys, 1 square inch of this area, how much force is that? Shear forces. How much shear force is there? 20, yes? That's not shear flow. That's a tau. Is that correct or not? Now, if I go to that strip here, which how many of that do I have? 5 of them. How much force is that strip? 100, yes or no? 20 times 5. Tau times 5. Is that correct or not? That's the shear flow. Did you get it? That's the amount of force per 1 unit length of the beam. Is that correct or not? Not the shear stress. Is that the tau? This, the entire force. Because look, this was 1,000. This is 10 inches. So how much force do you have here in this strip? Obviously, in that strip, you only have 1,000 divided by 10. Is that correct or not? Yes, it is. Kabil, are you with me? Yeah. What's the shear flow? What's the shear flow? Well, you said you are with me. I'm talking about shear flow. I'm explaining shear flow. What's the shear flow? I lost you. I don't want to lose you. So therefore, everybody understand what I mean. You don't want to lose me either. Is that correct or not? Yes? Therefore, that's exactly the point here, guys. Suddenly, this is very simple. 1 square inch is 20. Yes or no? 20, 20, 20, 20, 20. That is 100. That's the amount of force in that one strip. We call it shear force. Write it down. The amount of force per 1 unit length of the beam. If this was a beam, that would be 1 inch or 1 millimeter. Yes or no? Yes? How do we come up with the formula? What did I do here? I multiplied 20 by 5. Yes or no? What was 20? 20 was tau. What was this length? That length usually is the t of the beam. So if I take the tau multiplied by the t, I should end up with a q. Yes or no? So but the q therefore become equal to tau. What is tau is equal to? VQ over IT multiplied by t. T and t drops out, so only become VQ over I. Is that correct? I don't need any t there. Is that correct? Look at your handout now. Color handout. Look at the color handout, guys. Come on, guys. Look at the color. Do you see that shear flow there? What is there? Amount of force per unit length of the beam. Yes? Now, let's go back to this problem. Where is that force? That force is this force. If, let's say, the S is equal to 8 inches. So if the spacing of the beam, of the nail, are 8 inches apart, how many units do we have there? 8 units for each nail. Is that so? Half a spacing. Look what happened there, guys. If I give you a spacing of the nail is 8 inch, 8 inch, 8 inch apart, half of this force and half of this force goes to here. So yes? So this is S over 2, S over 2. So this 2 nail gets this much force. However, in 1 inch, how much force do I have? An inch, I have 100. Did you see that? Yes? So I have to multiply the Q. The Q is the amount of force in, look at it, 1 strip, yes? And if this, instead of 10 inch, this becomes 8 inch, how much force do I have? I have this 100 multiplied by 8. So therefore, force in each nail. This, I don't give this formula. You have to work it out yourself. You have to understand it. There is no formula for it. Only in the final, I give you every formula except that one. Because this is high school question. You have the amount of the force for 1 inch, and the spacing is the 8. You multiply it by 8. Is that correct or not? So that is total force from here. Half a spacing here. That's what I said. That half a spacing here. This for 1 inch is so much. I multiply it by that. So this becomes Q times S. Is that correct or not? However, that force is taken not by 1 nail. That will taken by 2 nails, so you divide that by number of the nail. This changes from problem to problem. You do it yourself. Is that correct? However, the key here, understanding how much force. This is what I'm saying one more time here. If I have, look at this blue line here. If I have 5 pounds here, going like this, or like that, is that correct or not? And I put a nail here at 8 each apart, I need 8 of this strip. Is that correct or not? So I multiply it by spacing. Is that correct or not? Then depends how many nails I have. I have 1, I divide it by 1. If I have 2 nails in that spacing, I divide it by 2. And now for our problem, let's go see what happened here. So for our problem, let's go to our problem. Now I'm going to erase that again one more time. Use your own re-registration of what I just said. I need the Q, I don't need the tau. Yes or no? We already calculate the tau here. Yes or no? Now I need the value of Q. So how do I calculate that? I can recalculate that by using VQ over I, or I can take the tau that I already calculated and multiply it by T. Is that correct or not? Yes? Correct? Either way. But since this is a new problem, you don't have the tau. If I do not ask you to calculate the Q's, let's do it again. So you put here Q equal to 3.5 times 10 to the power of 3. Then you put the same Q. You already did it in your, you put the same I there. The only thing you don't put is the T. Is that correct or not? Because T disappeared. Because instead of 1 square inch, now you are talking about the whole strip. So there is no T there. Everybody understand that? And then you calculate that one. For our problem, that ends up to be equal to, write it down, 14, because in the meter, it ends up to be 14,345 Newton per meter, or become 14.345, which is Newton per what? Per millimeter. Yes? Correct? Now, what's the spacing of the nail in this problem? Look at your handout. So you have to read the question, understand. What's the spacing here? Will not be in inch, will be in millimeter. What's the spacing of the nail is given to you? 70. So we need 70 of these strips. Yes or no? Correct? And each strips get 14 points. So you don't have to go metric, or you do metric or the same. You can use this for metric. You can use this for millimeter. Is that understand there? Yes or no? Correct? So forces in each nail become equal to 13.345 Newton per millimeter multiplied by what? Multiplied by spacing. What's the spacing? It's given in the problem. 70 millimeter apart. So multiplied by 70 millimeter. So millimeter and millimeter drops out. Notice you can do it in meter and meter. Everybody understand that? So that's the same thing. Divided by how many nail takes this force, because this is the spacing. This is how much force we are talking about. Is that correct or not? You see that? Yeah, yeah. That's what half is spacing, half is spacing. So how many nail is that in that spacing? 2. So 2 nail taking that one. So the force in each nail ends up to be equal to 502 Newton. So next time you go to the Home Depot, you will look at the boxes of the nail. You see the larger the nail get, the number goes larger. They write it in red. Let's start check it. So they have a 30 pound, they have a 50 pound, there are 100 pound nail. Depend on the size of the nail and how big they are, how it's supposed. Question.
It's still 14 Newton millimeters, right?
Yes.
For the force?
Yes,
Okay.
per 1,000. Because other one 14,000 Newton per meter, then 1 millimeter is 1,000 of them. So it's much less. Yes?
I'm just curious because it's.
No, I did both ways. Yeah. Yeah. Oh, I said, oh, those are mistakes. Those what are called mathematical error. If you do the same thing, you don't lose one point at all. I don't know whether you notice that people make mistakes. Still, I give them 100% that if that kind of mistake is that because you already calculate on top 14,000. I just I said it, but I wrote it wrong. Is that correct? That I do not consider a mistake. Everybody understand that. And you make that kind of mistake, is not. Your concept has to be correct. So if you don't know anything about the Q, you cannot do anything about that. Everybody understand that. Now, before we go any further, I want you to explain that a little bit further. Everybody, is that clear for everybody? So all you calculate the Q, which is the amount of force per one. No, it could be millimeter or inch, depend which system. You calculate for one, which is the shear flow, which is the amount for, is it from top view. Then you multiply it by spacing, then they divide by nail because depend on different scenario. Because notice that I can change that suddenly. Now, I want you to look at this problem, which is also symmetric. Look at next to it, there is another cross section, which is a little bit different. It's the same cross section, different way of making it. Exactly the same size, guys, but this time I did this. That's exactly the same size. Nothing is changing, guys. This is the same problem, except you put your wood, you can do it this way too. Yes or no? What I'm trying to tell you is still this problem works exactly the same as previous problem because the vertical shear is equal to, or we can do all of them in the same format, except the difference is this. You want to calculate the glue here. What should you cut out? Now you give me the answer. If this, look at your picture there. There is picture A and there is picture B. This is picture B. Is that correct or not? Yes? Actually, when you put the nail there, it's obvious. If I ask you to calculate this shear, here, the shear stress here, and the shear stress there, average shear stress there, are different from each other. Yes or no? Correct? So if I ask you to calculate the shear stress there, tau, for this one, or on average, how much shear stress do I have there? Because shear stress keeps changing from top to bottom, and this is a small quantity, so I can average it. Is that correct or not? Yes? What do you cut in order to understand? Remember, you need a Q, correct? Where is the Q? Where is the T? So I say, okay, tau, all right, I give you tau in your formula sheet equal to EQ over IT. We already talked about this too. That is obvious. Is that correct? That nothing changes that. The only thing changes between this problem and that problem is the value of Q or T, perhaps. Depends. We'll see there. What is the Q? Obviously. How do I cut it? Look, if I make a cut here, okay, I made a cut like I just said there, remember? But nothing being separated. That's not it good enough. Is that correct? So look there. I have to complete my scenario. Therefore, I have to make a cut like that. Everybody understand what I'm saying? So you need to cut it here and cut it here to get this piece move against the rest of the box. Is that correct or not? So the Q, rather than being this entire two, now the Q become this Q, which is a little bit smaller. Everybody, that's 120 by 20. The other one, that's what you were referencing, you guys back in the back. What's that? That was 160. This is 120 now. Is that correct or not? So that's the only difference. So you can do it that way. Now, can I put nail there? Of course, so look at the picture there. So instead of glue, if this one becomes too much or I cannot do it or we want to make it safer, then you put a nail like that, which you see it on the side of the beam. You see it here. The nail are going like that. Or sometimes the nail is here. Everybody sees it. Sometimes the nail are on top. Is that correct or not? Have you seen furniture like that? Is that correct? So that has to be there. So from side, but it's still the same thing. Q is there, same nail is there, but you have to cut two of them. Is that correct or not? And one more, how much time do we have? Or did I go over?
On time.
They're on time? Just give me one more second because I want to show you this in order to, just takes 1 minute there. Any question? Anybody raise a question? Yes.
Yeah, when we were calculating the shear flow on the top view, you got Q and I. Those obviously aren't the same Q and I from the cross section like this. Do you just calculate the Q and I at the top view, or
For which one?
for the last one we just did, where we calculated the shear flow for the nails?
That's the same.
It's the same Q and I.
Oh, yeah.
From
Everything is the same,
Okay.
except T disappears.
oh,
Except T disappears. Depends but where you are, though. You see, if you are, you see, this is the whole point. If you are here or here, the Q keep changing. So if that, but depends what Q did. Yes, but in general, Q is the same Q and I is the same I.
yeah. What value of Q did we use for the nails?
The Q of where we cut the nail, right?
The
Yeah.
Q of where you cut
Where
it.
you cut the nail. Okay.
Yeah, the nail will be at that level.
That part. That's
You see, the rest of it doesn't matter. I mean, you see, that's the whole idea. I hope you understand that part. In order this nail, I mean, the nail doesn't shear off there. Everybody understand that. The nail shear off here. Is that correct or not? That defined your Q. Okay?
Yeah.
All right? Everybody? Because that's the very basics. So, however, for the same cross-section, if I ask you to calculate tau max is where? Because I have asked that question. Tau max is there. So what do I need now? I need the entire here, the Q of this, Q of that, and Q of that. That's for tau max. But that is a different question. There is no nail there. There is but wood is there. Is that correct or not? in the nail, depend when, that's what I'm saying that. Look, this nail is going to shear off like that. This piece, that's exactly your understanding here. This piece wants to come like that, got it separated. So this nail, which is here, is going to shear off this way. This way, is that correct or not? So this, again, is our horizontal shear. Is that's the whole thing there, yes? We do it vertically, we do it horizontally. Don't mistake the two together because there is one like this, there is one like that, remember that. So we are talking about two different things. For the nailing, we need this one. For the stress in the cross section, problem number 1 was about this. Problem number 3 is about that. Is that understood? There are two are equal and the same magnitude, but there are in the cross section stress going there, in the beam stress going that way. So therefore, now one more question. I'm sorry, I have to finish this because without saying that. Now I'll just give you, because I have given this example, which is actually part of your homework too. So let's say you put a box like this. This is the cross section, it's some sort of furniture or something. Yes or no? Yes. If I want to calculate glue here, what do I need? That's exactly the question you asked, my friend, or for everybody. If I want to find that glue at A, what is my Q, what is my T? Just tell me, yes. I have to say, I don't have even to go there because these two could be different sides or the same side. All I have to do, this is my, because this is pieces coming out like this. I have a piece of material here, glued here. I put this here. You see, it's going to shear off there. Is that correct or not? Therefore, this is your Q. This is your T. Is that correct? Now I can put a nail there instead. Yes? So I can do that. I don't need to do two because each one is separate. Remember that problem? I have to do cut both of them. Here I have to cut only one. Now be careful here. For this one, if it is the same size and everything the same, which is usually the case, you don't have to worry about it because it's the same. Is that correct? However, you may nail it here too. For that nailing, what's your Q?
Entire.
Answer me. If you answer me, then you are home free from there. Everybody should have some idea there. So the entire top. You see, you want to cut it out. Remember piece of cake there? I really not was joking. That way you can understand it. Take the whole thing out. How? You have to cut it like that. Yes? So in other words, this nail is good. It's strong enough. This nail is strong enough. This nail is shearing off. In order this nail to shear off, this piece has to be cut out. You get a bigger piece of cake. So let's go at that. All right? Did you get it? All right. Good luck. Your homework is